Hello guys, welcome to JG Chemistry. Guys, I have already uploaded video on Cram's rule and Redox rule. If you haven't seen that video and you would like to know and solve the problems on it, you can refer those videos. You can find the link of those videos in the description box of this video. In today's video, we are going to learn the conformation of di-substituted cyclohexane, and it is one of the important topic for all the competitive exams post MSc and even for the MSc students. Let's begin. So there are total 3 or 4 possible formulas one can have. One is 1,2-dimethyl cyclohexane. Other possibility is you may have 1,4-dimethyl cyclohexane and 1,3-dimethyl cyclohexane. So in this we will first see 1,2-dimethyl cyclohexane. What is the correct conformation to draw it? We know that the stability of the cyclohexane exists in the chair form as compared to the board form. So you have to draw the chair conformation of it. Now the position of the methyl group, you can have here 1 and 2 position, you can see methyl group. Now 2 possible isomers are there. It may be cis or it may be trans. If they ask you to draw the cis isomer of 1,2-dimethyl, then cis you can easily identify by making the 2 bulky groups on the same side. So you can notice here this methyl is also above the plane, the other methyl is also above the plane. Both methyls are above the plane, means this is a cis isomer at 1,2 position. And if you notice this A and E position is for the equatorial, as it you can see away from the chair, and other is the A axial conformation, axial position of this methyl group. So 2 positions, one is equatorial. So all away from the chair, like you will have equatorial position, and all vertical lines you can say is axial position. So that we will see in further examples, isomers. Now one point, so this isomer for cis 1,2, it may be axial equatorial isomer, or you can say equatorial axial if you flip this chair. So after flipping this chair, the axial position will become equatorial and the equatorial position will become axial. So you have either possibility AE or EA, both are same. So basically for 1,2-dimethyl, for cis it is AE or EA isomer position. Now if you notice, I have drawn this green color dotted line which says that there is a strong 1,3 diaxial interaction. If you notice the position of hydrogen and methyl with respect to each other, methyl is 1, 2 and 3. So the position is 1, 3 to each other, and therefore you have this 1,3 diaxial interaction here. There are total 2. If you flip the ring, the other side also you will have this equatorial will become axial and will show the 1,3 diaxial interaction. Now if they ask you to draw the trans conformation of 1,2 position, means the 2 methyl group has to be opposite to each other. So one possibility, the 2 methyls are at 1,2 position opposite at axial position, vertical line. But in this you can notice there are here in the 2-dimensional diagram, you can see here you have 1,3 diaxial interaction. Total 4,1,3 diaxial interaction will be there after flipping of the chair. So this makes the isomer trans as unstable or less stable. So the other possibility is to draw the trans 1,2-dimethyl cyclohexane is you can draw both the methyl at equatorial position. Here also it is trans only. One methyl is above the plane, the other methyl is below the plane. So the 2 are trans to each other but at equatorial position. And at equatorial position, you don't have any 1,3 diaxial interaction with this methyl. So this makes this isomer is the preferred conformation of trans 1,2-dimethyl cyclohexane, and it is more stable. And if you compare all the 3, the total and the most preferred conformation on the stable conformation is, you can see, is EE, then comes the AE or EA, and then least stable is AA. This is a stability order in general for the cyclohexane derivatives, especially for 1,2 position. Or 1,3 position also you can find the same order, and 1,4 also. Now few points I have written here, we'll just go through it. We have already covered that Cis 1,2-dimethyl is either going to be AE or EA, and there are total 2,1,3-diaxial methyl hydrogen interactions. While in trans, EE isomer is going to exist and there are no axial interaction is there. For trans AA isomer, there are total 413 diaxial interactions. So that means it is having the great stain, and so it is the less stable than compared to the AE isomer. So basically for cis you are going to draw AE or EA for 1, 2, and for trans you are going to draw EE isomer, EE conformation. So whenever they ask you to draw a trans 1,2-dimethyl cyclohexane, this is the preferred conformation where the two positions are on equatorial. Similarly, you can find 1,4-dimethyl cyclohexane. The two methyls are 1, 2, 3, 4, 1, 4 position to each other. One methyl is axial, another is equatorial. Both are above the plane. So it may be AE. If you flip the ring, it will become EA. The axial will convert into equatorial. The equatorial will convert into axial. And so total, again, you will find here 2,1,3 methyl hydrogen diaxial interaction for cis 1,4 isomer. Now, if they ask you to draw the 1,4 isomer, 1,4 isomer, again, the possibility is for trans 1,4, either two may be axial position. So again, you will find total 4,1,3 methyl hydrogen interaction after flipping, and that makes it less stable. The other possibility is you can draw both at equatorial position for trans 1,4. That makes more stable because here you don't have any 1,3 diaxial interaction. So again, the order of the stability is EE is most stable, then AE or EA, and the least stable is AA. You can notice 1, 2 and 1, 4 both are having the same conformation AE and EA, while for cis and while for trans it is the EE. So this is the trick. Whenever they ask you to draw 1, 2 and 1, 4 dimethyl cyclohexane is going to be, you have to draw AE, and if you learn this only, you can draw the trans isomer as EE, and in other case the 1,3 is going to be just opposite to this. We can notice that in this example. So 1,3 dimethyl cyclohexane, you can notice this is a reverse of the previous two example. Now in this, the cis isomer are either it is AA or EE. At 1,3 position, EE is more stable because of there is no 1,3 diaxial interaction as compared to AA position. While for trans, you have only possibility either AE or EA, and you have total 2,1,3 diaxial interaction will be there. So this is just opposite. In the previous two cases, 1, 2 and 1, 4, the cis isomer was AE or EA, while 1,3 is having EE here. And for trans, it was EE. Now in case of 1,3, it is AE or EA. So if you learn one, you can draw the rest of all other isomers by using that trick. Now we'll see some few examples where you have, instead of methyl, you have a bulky group called tertiary butyl group. Let's say they ask you to draw the trans 1,3 tertiary butyl cyclohexane. The position is 1,3, and they are saying to you to draw trans, means the two are opposite to each other. So one is coming at axial, other is going to the equatorial, or vice versa. Now in this case, again, you can find that there is a severe 1,3 diaxial interaction as compared to the 1,3 dimethyl isomer. So this makes it least stable and has to convert it into the other conformation called the twisted boat conformation, and where you can notice the two tertiary butyl groups are opposite to each other in this conformation, which is away, and there is no 1,3 diaxial interaction because hydrogen is also going away from each other. So in this case, it is avoiding the severe 1,3 diaxial interaction. We know that though the chair form is more stable as compared to boat, but in this case, this is going to be exception where the twisted boat conformation is more stable as compared to the chair conformation. So this is again, all exceptions are important, especially for the exams or competitive exams. So this is because of the unvariable steric interaction between the tertiary group and the hydrogen that is converting it into the twisted boat conformation. If they ask you to draw the cis 1,3 tertiary, that is going to be the chair conformation only, because in that case you can draw the two at equatorial position. If they ask you to draw the cis 1,4 tertiary cyclohexane, cis means the two are on the same side. In this, one is going to be axial and has the 1,3 diaxial interaction that makes it highly unstable, this chair form. So it is going to convert into the boat conformation, where you can notice the two are opposite to each other. The two tertiary are opposite to each other. They are away from each other, and there is no such 1,3 diaxial interaction in this boat conformation. And so here also the boat conformation of cis 1,4 ditertiary cyclohexane is more stable than the chair conformation. While if you draw the trans 1,4 tertiary cyclohexane, you can draw the two at equatorial position, and that makes the chair conformation itself as a stable conformation. So the two examples are the exceptions, and you can practice some more example based on this concept. Happy learning.